Hello and welcome back to my YouTube channel MS Maths. In this video, we are going to discuss about the Z transformation. This is the part second for this topic. We have also discussed the definition, properties, and some basic formulas in our previous videos. So you should watch that video to concept to clear the concept of the Z transformation. It is the part two. Now, in this video, we are going to discuss properties and some basic formulas. There, we will discuss two property. That is the one is the linearity property, and second one is the scaling or damping property. And we will also discuss some problems and some standard formula for this property. Now come to the first property. This is the linearity property. Linearity property is nothing but if I am multiplying, like linearity properties says that if you have a z transformation a of a function, if you are going to adding to function and applying the z transformation after adding the function and then applying the z transformation, or that is the equal to firstly finding the z transformation of all the function and then add all the all the results, that is equals. So basically it is nothing but if you are going to calculate the z transform after the addition or before the addition, that is equal. This is the linearity property. Now we'll use some basic definition. So it is nothing but a definition of z transform. The definition of Z transform says that the Z transform of a function is nothing but a series n equals 0 to infinite un z power minus n. And un is nothing but a discrete series. It is nothing but a discrete function also. You can see the discrete function or discrete sequence. Okay. So here we have the un is this for this. Like I will start from left hand side. Left hand side is says that z transform of a f of n plus b g of n. We have two discrete sequences. Now how can we start? How can we proceed forward? Basically from here it is our un. Okay, here un is nothing but a f of n plus b g of n, and we can proceed forward like this by the definition, by using the definition of the z transform. It is nothing but z transform of a of fn plus b of gn is equals to summation n equals 0 to infinite a f of n plus b g of n into z power minus. This z and this z is different. This is the operator z transform and this is the complex variable. Please note that, and please defer the sign, sign to right. Okay. Now here I can multiply these things. Okay, like a is a constant, and we can write outside. So this is the summation n equals 0 to infinite f of n z power minus n, plus b is also constant, we can take outside. It is n equals to 0 to infinite g of n z power minus n. Now you can see here it is nothing but of definition. It is nothing but a definition. So is the definition, then we can easily write it a z transform of f of n. Similarly, it is nothing but b z transform of g of n, and it is our left hand side. It means if you have two functions and before adding that function, if we are calculating the z transform and to get of z transformation and then add, that result is equal to the z transform of the addition of the function. Okay, so this is the meaning of the linearity property. Now come to the scaling property, or sometimes it is known as damping property. So damping property says that if you have a power n or a power minus n is multiply with your function, multiplying with your discrete sequence of the nth term of the discrete sequence, then what is the result and what's the z transform? Like this is the telling about that. Scaling means you can scale that function by multiplying the a or dividing the a. You can see here the result. Okay, now we'll use the definition of this, definition of the function like this. First of all, I am going to prove first. So basically the first result is nothing but z transform of a power minus n f of n is equals to, like, this is the nothing but z transform of a z. Like a is multiplying when the a power minus n is a multiplication of the function. Here un is nothing but this function. Okay, now it is implies that un is nothing but a power minus n f of n. And by using the definition, z transformation of a power minus n f of n is nothing but summation un. Un is a power minus n f of n z power minus n. Now this is the z. This, like, I can write n tends n 0 to infinite, n equals to 0 to infinite, a power minus n, and I can write both the things here. Now it is the transformation of un when it is a it is the transformation of un, and the function is in only a complex variable. Now I can write it is nothing but it is a transformation of az. Here is a z is az. So basically I can write this is the function of nz. It means if you have a power minus n is in a multiplication, then in the transformation of the function, you can multiply all the z with a, all the z with a. Okay, all the z with a. If you have multiplying a power n with a function, you can put in a transformation of that function a in divide, a in denominator, like this. I'm just taking an example, z1. Okay, now if you have z power an, z power minus an into 1, we know that z transformation of 1 is nothing but z upon z minus 1. But a power minus n is multiplication with 1. For a function un is nothing but 1. 1 is nothing but a power n into 1, a power minus n into 1. Then due to a power minus n is a multiplication with this, with the term, and we have a property, we have a damping property. We have to multiply for this a power minus n 1 to calculate the z transform of this. It is nothing but a into z upon a into z minus 1. This is the z transformation. Okay, this is the function. Like, remove this and then firstly calculate the z transform of that original function, and then a power minus n, it will react like this. Next thing is here, if z transform a power n f of n is multiplying with the function, similarly un is nothing but a power n f of n. It means that implies that summation n equals 0 to infinite a power n f of n z power minus n is here, and I can write it is nothing but n equals 0 to infinite f of n and z upon n power minus n. Okay, if I'm taking like in a denominator, then z by a power n is, and it is nothing but f of z by a. Like this, I'm taking like the example. This is the first example. This is the second example. Z transform of a power n, or I'm just taking a power n is not like 2 power n into 1. So now, firstly cut it and find the z transform of this. It is nothing but z over z minus 1. Now 2 is here, and a means a is 2. A is 2. It means it is nothing but a z by 2. Z by 2 minus 1, and it is nothing but z upon z minus 2. Z upon z minus 2. Okay, we can write this thing. So you can see here it is nothing but z power 2 power n. We know that a power n is nothing but 1 upon a minus. So we can calculate from different types. So I think you don't see like this. Okay, you can see now. So this is nothing but the thing. Okay, it is the important. Basically, by this way we can easily calculate the things like this. Now come to the next question and next problem. By using this, we can find some standard formula like this. We want to calculate the z transformation of a power n, and it means cos of n theta is cos of n theta. We know that the cos of n theta, that transform of the cos of n theta, but a power n is in a multiplication. If a power n is in multiplication, by using the damping, we can easily calculate. By using the damping, we can easily calculate that is the upon a. Okay, and if there is a minus n, then multiply by a with z. Simple thing is here. So this is the z transform of the cos of nx. It is nothing but z into z minus cos of x over z square minus 2 cos x plus 1. And now z a power n cos of n theta is here. Okay, I'm writing in the x. Okay, so it is nothing but z. You can write theta like theta. Theta is here. So it is nothing but z by a. By using, we can write by using scaling property or by using damping. By using damping property of the z transform. So z by a, and it is also z by a minus cos of theta upon z by a whole square plus 2. 2z is here. Okay, 2z is here. Basically 2z is here. 2 into z by a cos of theta plus 1. And by this, we can take LCM and we will get z over z minus a of cos theta over z square minus 2az cos of theta plus a square. Okay, so this is the general term. And like next thing is here, you can calculate this is also. This is the nothing but the z transform of the sine x. So basically z transform of the sine nx is nothing but writing this theta here. Okay, no problem. So z transform of the n theta, that is z sine theta. Okay, z sine theta upon z square minus 2 cos of theta plus a square. 2 cos z theta. That 2 z cos theta plus 1. Now a power n is in multiplication. It means by damping property, by the damping property of the z transform, we will divide this a such a manner z by a whole square minus 2 z by a cos of theta plus a square. There is no a. I think there is no a. There is a mistake. Plus 1. Okay, it's plus 1. So basically by using this, and you can solve also this thing z plus, then if you are solving this thing, like is nothing but z sine of theta and a square is here. So basically z square minus 2za cos of theta plus a square, and a is here. So this is the correct thing. Okay, I think there is a typo. So basically this type, like by this method and by this damping property, we can easily calculate all the things easily. So thanks for watching my video. Keep watching MS Maths for this types of video and such types of video lectures. You can subscribe my channel and you can get all the things easily by like higher mathematics, for higher mathematics and physics. So thank you. Bye bye.